In this video, I want to look at the reactions of acid chlorides with various compounds to form carboxylic acid derivatives. Now, the acid chlorides themselves are made from carboxylic acids and thionyl chloride, as we discussed earlier. But now that we have the acid chloride, what can we do with it? Well, an acid chloride will react with alcohol, for example, to give an ester very nicely. And we simply use the oxygen of the alcohol as the nucleophile, attack the carbonyl, and this is going to, of course, give us our tetrahedral intermediate. And that tetrahedral intermediate will fall apart because the chloride is a nice leaving group. So we'll come down, reform the carbonyl, kick out the chloride, and what this gives us is our ester, but it's protonated. Now we need some base to get rid of that proton, and what base is around? Well, the best base around is just excess alcohol, and so we'll throw some extra ethanol in there, or use some extra ethanol, and deprotonate, and this will give us our final ester product. And of course, the proton ends up on the ethanol, and the chloride is around in solution as well. Now, this is a fine reaction, but it turns out you can make this reaction better by catalyzing it. And how do you catalyze it? Well, you do that by throwing in a better base, which happens to be also a nucleophile, and that base is pyridine. So let's do the same reaction with pyridine present. And the pyridine is actually going to serve as a dual role. It's going to be the catalyst, but it's also going to be the base. And it's a better base than ethanol, and this combination actually makes the whole reaction go faster. So we're going to do the same reaction, but we're going to do it in the presence of pyridine as a base. Now, when you have this and you look at it, the problem here is ethanol is no longer the best nucleophile. Pyridine is the best nucleophile, so it's going to change the mechanism completely. The reaction is going to take place is the pyridine is going to attack the carbonyl, and we're going to form this strange-looking. Oh, that didn't draw out very well. Let me redraw that. Here's this strange-looking tetrahedral intermediate with a pyridine on here. Now, see, the beauty of the pyridine is it can't form an amide because there's no way to get rid of that positive charge. So the pyridine is not going to form a stable compound, but it forms a nice intermediate. And that nice intermediate, when we kick out our chloride, is this guy here, which has got the carbonyl with that positive charged nitrogen on it. Well, that pyridine is a very good leaving group. It's about as good as leaving group as the chloride, actually, not quite. But it means that this species right here now is very reactive with respect to the ethanol. So we'll now bring in the ethanol as a reactant. Let me just, here's our ethanol, and it's simply, of course, going to attack a carbonyl again. Oops, didn't do that right. Attack the carbonyl again, and push the electrons out on the oxygen. And here's our new tetrahedral intermediate, and this is now going to kick out the pyridine and give us our protonated. Going to give us our protonated ester again, and you can see what's coming. And now we'll use the pyridine in its second role. We're going to use it as a base. And this final step will give us our final ethanol. And let's see. What happened there? Yeah, I didn't have that arrow long enough. And here's our final product here, the ester, and the pyridine is served as the base. So this reaction is faster, even though you have to deal with this pyridine. So whether you use it or not would depend upon how well your reaction worked without using the pyridine. But it is a new wrinkle on the whole mechanism. So that's forming an ester. How about an amide? So let me reload the page, and we're going to go through this with an amine. Now, an amine, of course, is a good base, and we don't need a catalyst for the amine because it's plenty nucleophilic already. So these will react like a whoop, I just drew that arrow wrong. Missed the bond. I missed the atom. Hit the bond. I'm having a terrible time here. Okay. Get my arrow. Okay, so we're going to draw the arrow, attack the carbonyl, electrons out on the oxygen. Here's the tetrahedral intermediate. Kick out that chloride. And we have a protonated amine. And that protonated amine, of course, the base that's sitting around is the starting material. And so we'll use another mole of the starting material to deprotonate. And there's our final product. Now, the interesting thing is that the ethylamine has served two roles. It's our reagent for forming the amide, but we've also used it as the base to pick up the proton of the HCl. Now this means if you're going to do this reaction, you have to throw in 2 moles of the base. Because if you threw in only 1 mole, you'd only get a half a yield because you need 2 moles per reaction. Now this sometimes can be a problem if your amine is, let's say, expensive or rare. You wouldn't want to use 2 moles of it because it would be wasteful. So sometimes people will do this reaction. They'll throw some other base in, which is either less nucleophilic than your amine, or can't form an amide. Like you could use pyridine again, or sometimes people just you can actually do this reaction with hydroxide if you're quick, because the amine is a much better nucleophile even than hydroxide. So anyway, you do need your amine and some base, and the easiest thing is just to use 2 moles of the amine. So okay, so that's the amide. We have 1 more of these to do. I want to go through the synthesis of an anhydride. Now the anhydride is the reaction between the acid chloride and a carboxylic acid. So let's draw out a carboxylic acid. And I don't want to do acetic acid because it would be the same. So let's do something else. Well, I'll just make it propionic acid. So here we have this is ethyl change versus methyl. So this is going to do the same thing, whereas your oxygen is going to come over here and attack. Well, except I'm doing this backwards. Silly me. The carbonyl oxygen is the one that's going to attack. This will give us our first intermediate, and then again the same thing is going to happen, is that the oxygen is going to come back, kick out that chloride, and give us our protonated product. And now again we need a base to pull this off. And the problem here is, as you can see, we don't really have a very good base around here. Because the carboxylic acid itself is certainly not a very good base, and this reaction basically doesn't work very well unless you use some other external base. I'll draw the chloride here just for the sake of argument, but it's a really terrible base, so it doesn't work that well. So this reaction, it works. Here's our anhydride, but it's not going to work very well. So the secret, of course, on this is to again go back and use that pyridine as the base. And so if you're going to do this again, let's go through and do it with pyridine. And so here's our we'll go back and put our pyridine in, and we need our carboxylic acid. Should we do the same one, or should we do a different one? I don't know, just for the sake of argument. Okay. Okay, we'll do what do we do? Let's just do something different for the general hell of it. Okay, here's just make a different carboxylic acid. So the first step this time is going to be the nitrogen attacks again the carbonyl, forming that same kind of intermediate that we had when we did this the first time. We got the same ugly drawing from Oscar. I don't know why Oscar does that first drawing so poorly. And again, we're going to kick out the chloride and make that pyridine-based intermediate. Where's my arrow? Okay, there's this, and now this is going to react with the other acid. So let me get a reaction arrow down here. So here we go. Actually, better make this a little bit smaller. I'm going to get in trouble. Okay, so now what's going to happen is this carbonyl is going to attack right here, new tetrahedral intermediate. Okay, yeah, that arrow's a little long. Okay, and now this tetrahedral intermediate is going to fall apart, kicking out the pyridine. Now this reaction is all much faster because we've taken care of our base problem. And then the last thing is to get rid of the proton, and our pyridine is right there. So again, our pyridine is playing this dual role as catalyst and as base. And so that arrow's in the wrong place. Can you see that? I drew it from the atom instead of the bond. Got to be careful. Hit the bond. I just did it again. There, come on, there's the bond. When they get small, it's sometimes difficult to get the right one. And there's our final product. This is our final anhydride, and our pyridine has picked up the proton, and so this reaction would work really well. So that's a good synthesis of an acid anhydride starting with an acid chloride. And so this, as you can see, this is a very general scheme, and the reactions work quite well. And so you can make esters, amides, anhydrides, all starting with acid chlorides. The acid chlorides themselves, again, come from thionyl chloride.